Alright, hell yeah. Alright, so for once and for all, I'm going to figure out Centripetal and Centrifugal. I don't even know if I'm using that words right. I don't even care. I mean, at the end of the day, all we want to know is so we have something spinning. Let's say it's the Earth, and then we're on top of it, on the equator, and then we're spinning. Well, we're basically getting flung off of it. And then the other scenario is like the roller coaster. You know what I mean? You have a circle that's spinning, and then you're on the inside. You know what I mean? Let's say in a seated position, like in a chair of some sort. It's a roller coaster, and you know what I mean. It feels like you're gonna, you're heavier. It feels like you're heavier in this case. It feels like you're lighter in this case. And then so what we want to use is the F equals ma. Now, and I don't know. I'm starting this video from like, hey, I know I can figure it out, but you know what I mean. Let's say I don't know. So we're going to use the Earth. The Earth has a big mass of the Earth, and then we have the little mass. That's the mass of us. And so even for like in the common one, if we are standing on the Earth, you know what I mean, we'll have a vector, our weight. Our weight is mg. You see this a lot in a lot of different problems. You know what I mean? Something with mass has a weight, it's near the Earth. You know what I mean? And the first thing is just like, well, why is this? Well, it's because you have a force of gravity that's the gravitational constant, mass of u, mass of the Earth divided by the radius of the Earth squared. Now the most important thing is, where does this equation go in F equals ma? Well, on this side we say, hey, we sum the forces, and that's going to equal to the mass times acceleration. And so what I like to do is throw eyeballs on this side, because what you're looking for is like, hey, are we accelerating? You know what I mean? So when we're standing on the Earth, it's like, well, no. Well, I mean, we're not. I mean, and we're talking about the up and down direction. Are we accelerating in the up and down direction? Well, shoot. You know, like obviously we are if we know rotational. Rotational things, because theoretically we want to be moving tangential. Like we have a tangential velocity when we're on the Earth spinning at the equator. But it just happens to be that the Earth is falling away, and so to stay on this ride, we actually have to be moving 90 degrees to the tangential direction. So we are moving tangential, I get it, but then as we want to be just moving tangentially, but we're not. We actually fall down towards, the Earth is falling underneath our feet, and to catch up with it, oh, and that's kind of cool. That's kind of the elevator effect. You know what I mean? If you have an elevator that has velocity 0, you're standing on it, and then a couple seconds later, heck yeah, it's down here. Well, it's like you're gonna feel maybe, and if it got down there real fast, heck yeah, you're still up in the air right there. Or you just feel, maybe you are attached to it, you just feel less heavy as it got up to speed. You know what I mean? From 0 to speed in like a change in time of like 1 second. You know what I mean? And then you feel a little bit lighter. All right, so we have that, and for this scenario, hey, we don't see any acceleration, so that's 0. But we still, like over here, I do a little textbook. You know what I mean? Because there are different forces in the universe. Like 1 is gravity, 2 is like electrical force. You know, the electricity between a proton. I don't even want to say anything. But then the other one is like bonds between elementary bonds. You know what I mean? You have 2 atoms that come together, form a molecule. So you do have molecular bonds and atomic bonds. But anyway, so just a lot of things have force, and if you can identify, so that's this thing, is like, this is more like, hey, we want to look for motion, and this side is identifying. Alright, identifying what things in the universe cause force or have force. And the force of gravity is like all around us, you know what I mean? It could be the gravity of this earth. It could be the gravity of that sun. It could be the gravity of that moon. It could be a gravity of other stars, you know what I mean? But obviously gravity, for the most part, is only seriously affected by the things that, you know, the earth, the sun, and the moon. Those are the things that are you know, in our solar system affect us. I don't know if the other planets, like Mars, actually has too much influence over, you know, even tide. I don't know. It'd be fascinating if it had too much influence over tides. Jupiter's huge, you know what I mean? I wonder if... But I think Jupiter is way farther away than... yeah, that'd be a great equation. You mean like... Jupiter compared to Mars, which has, is the gravitational force even close to being the same? But anyway, so this equation for force of gravity goes in this side right here. Alright, so this is kind of part 2 of rotational, you know, problems, where if you do fall away, and it's kind of cool to do this, you know, you should be able to do this like every time. So what we're going to say is the Earth is fairly flat, but no, it's kind of curved a little bit. You know what I mean? And then so this is the tangential, and then the Earth, you know, is underneath us. And so the other way to draw this is just draw like that. Here's the center of the Earth. Here is the radius of the Earth. And we want to move tangentially, but we're not. We're moving slightly in a curved path. So what I do is do a change in time of 1 second. And you don't even need the radius of the Earth to do this. You could just have a radius of 1 meter. You know what I mean? And the change in time of like 1,000ths of a second, 0.001 second, that's going to be our change in time. Now, things that are moving in a circle want to just move tangentially. But if they're stuck physically to the circle they're moving, they're going to be moving in an arc. But we're going to take a very, very small arc. And in a circle, you got 360 degrees. You also have 2 pi radians. That's another way to say 1 revolution of a circle. 2 pi radians is the same thing, you know, as degrees are. You know what I mean? It's just 6.28 divvied up across the whole thing. So what we do here is we say, hey, well this path is more or less, or what do we do? We say this is also 1 meter, and then we bring this down. And when we do that, we get this distance right here, which if this is our angle, you know what I mean? This is the sine part. This is the cosine part. So this distance right here will be 1 meter cosine of this angle. And that's going to be this distance. What we're interested in is this little d right here. Well, that's going to be 1 meter minus that. You know what I mean? So it's basically r minus r cosine theta. This comes up a lot. And that's just the remaining distance right here. What happens is that we do have some velocity, and I'm just going to say our velocity is 1 meter per second. Also, we have a revolution of 1 radians per second. 1 radian per second times radius gives us something normal. Radians times radius is something normal. and our radius is 1 meter. So we have 1 radian per second times 1 meter. That's 1 meter per second. This is just kind of a good one to do, because what we want to find out is that we have an acceleration, which is a change in velocity, change in time. And this is the acceleration normal. It's in the normal direction, and it's toward the center of the radius. So if we say, hey, this is positive radius, like this is positive r this way, well, we're going to have an acceleration in the negative direction. So we're going to have negative acceleration. So we're going to find the change in velocity, change in time, and it's going to be in the negative direction. So how do we find the change in velocity? Well, we know our change in time. We already said our change in time is 0.001 second. But what we do is we find our velocity by saying, hey, well, this is what you do. So at this point initial, you have no velocity towards the center of the circle. Your velocity in the normal direction is 0. You're going purely tangential. Cool. Now, it seems like you're just always moving tangential, but that's not the case. You have to pick this as kind of your datum, and then 1 second later, you should have been moving tangentially, but you're not. You're over here. And as long as you make this theta really tiny, this direction over, d, is the same distance in the same direction towards the center. So in a thousandth of a second, you move this distance d that way. And so if you move towards the center of the circle, you must have had velocity towards the center. Because right here you have 0 velocity. And so the first equation is like, hey, you have to get the velocity average, which is the distance you traveled. Distance divided by time is velocity, times this 0.001 seconds. Cool. And that distance this distance is right here. So, and then once you find that velocity average, well, then you can know that we started with 0, and we must get to some velocity max. And so velocity max is just 2 times velocity average. And this is the same scenario. I use this example. I think it's a good one. If you drive for an hour and you start at 0 miles per hour and then slowly work up to 60 miles per hour, you know what I mean? Over the course, 60 miles per hour, over the course of a whole hour, you go from 0 to slowly increasing your speed to 60, and you travel for 1 hour. Now the question is, how far did you go? Well, you have to figure out your average speed. You were 0 here, 60 max, and then you slowly increase. So your average speed is 30 miles per hour, and it's basically like traveling 30 miles per hour for that hour, so you went 30 miles. And so the same scenario here, just in reverse. We found our average speed. We knew we started at 0 miles per hour towards the radius. Our max speed, that's what we're interested in, is 2 times the average. Now, why are we interested in our max speed? Because the acceleration, definitionally, is change in velocity, change in time. We need to know our change in velocity. So we went from 0 to 60 in this scenario. We go from 0 to our max velocity in that scenario. And change in time comes up again, because our acceleration, normal, is going to be that velocity max, that's our change in velocity, divided by that 0.001 seconds. So where was the first place this change in time came up? Well, to get the velocity average, we had to cross that distance in 0.001 seconds. Then we take that and multiply by 2, and then divide by that change in seconds again, and that gives us our acceleration normal. And then we should just know that acceleration normal is negative r omega squared. And heck yeah. So this is kind of the first step in the game. And then we got to take this acceleration and be like, well, do we put it here? Or do we say that this accelerate? Yeah, I think we do. You know what I mean? That's the hunch. I mean, it says acceleration. I mean, doesn't that go in this side of the equation? You know what I mean? And they're vectors, so we have like, hey, the sum of the forces is equal to mass. Couldn't you say it's the sum of the accelerations? You know what I mean? Because isn't force, a vector force, equal to mass times the acceleration? Now, all right, so let's do this one, and we'll just kind of go nice and slow. But the bummer thing about this one is that we have a radius of 1, and our angular acceleration is 1. So basically, we're going to have 1 times 1 squared. So our acceleration in the normal direction should just be 1. And let's see if it is. So we're going to have our distance d is 1 minus, yeah, I'm in degrees, 1 minus 1 cosine. Now, we need to, yeah. So this angle, we need to figure out what this angle is. Because if we're going 1 radian per second, yeah, that's the first thing. So our speed is 1 radian per second. But guess how much we travel for? We're only going to travel for 0.001 seconds. So times 0.001. Hey, look at that. We go 0.001 radians. Okay, so that's the angle that we travel. And all right, sweet. So once we know the angle, that's going to be, oh, and I need to switch to radians. So 1 minus cosine 0.001. Okay, so that's my angle in radians. And oh, well, we already put it in. So no, this is d. So we're going to store that as alpha d. So yeah, 1 minus 1 cosine of 0.001 radians. It is our distance d. And then what was the other equation that had d in it? Right here. So we're going to get our velocity average by dividing by 0.001. And then once we get the velocity average, we're going to multiply by 2 to get the velocity max. Change in velocity, change in time is that velocity max divided by 0.001. And heck yeah, we get an acceleration of 0.999. So let's do this one more time where same thing, just a really small angle. And our acceleration is r omega squared. So what do you want to multiply together? Do you want to say our radians is 3 radians per second? And then so that the omega squared would be 9. And then we're going to multiply 9 by, let's multiply 9 by 5 meters. So we have 5 meters. This is our length that we're rotating. Straight down. This is our distance d, tiny distance d. This is our angle theta. And our change in time is 0.001 seconds, thousandths of a second. Thousandths of a second times 3 radians per second. 0.001 times 3. So this is how many radians we're traveling. I'm going to store that as alpha theta. I'm going to go 5 minus 5 cosine alpha theta. This is our distance d, stored as distance d. And then distance d divided by the change in time, that's going to be our velocity average. Cool, now we got our velocity average. Going to store that as w. I'm going to go multiplied by 2. I'm going to store that as alpha u. That's our velocity max. So now we have our max velocity, and we know our change in velocity is our velocity max. And we're going to find our acceleration. That's going to be change in velocity, change in t. So we're going to do that divided by, again, the 0.001. Cool. We get an acceleration of 44.99, and that's what we would expect. We have 5 meters. Omega is 3 radians per second squared, and we get 5 times 9, 45. Cool. So we get 45 meters per second squared. And that's our acceleration. So that is a total check on reality. So now what we want to do is Well, I think we should go back to the problem of the Earth. You know what I mean? So we have an Earth, and then I'm just going to say this is, this is the North Pole. We have a bird's eye view. This is the equator. I have no idea which direction the Earth spins. You know what I mean? So I'm just going to guess this way and be totally wrong. That'd be interesting. You know what I mean? Does the Earth... It's too hard for me to even fathom. You know what I mean? It'd be too easy just to get it wrong. But let's see. If north is this way, and then east is to the right on a map, and in the east you have New York City. New York City sees the sun first. The sun doesn't move, but the Earth rotates. So the Earth is rotating this way because the New York skyscrapers are catching up to the sun. Once they do, they'll pass it, and then I'll see some light. So there you go. So if my thumb's north, we are spinning... Oh yeah, so the Earth spins right-hand rule. So that's pretty good. It spins counterclockwise. So if this is north, yeah, I think I got it right. Okay, so and what we want to know, and I guess we have to do this. So if we're standing on the Earth, we have a normal force up. And then we have a weight force, W, that's mg. And again, where the hell is this mg? If all we have is this, if we just have the Earth's mass, then we have F equals ma. Fg is gravitational constant, mass of me, mass of the Earth, radius of the Earth squared. So this part goes in that side of the equation. So we have me divided by the radius of the Earth squared is equal to the mass times acceleration. Now everyone talks about, hey, what's the acceleration of gravity? So you're solving for this side. You bring the m downstairs, and then these m's cancel, and then these three things are 9.8. You know what I mean? Gravitational constant, 6.66 times 10 to the negative 11. Mass of the Earth, 5.94 times 10 to the 24. Divided by radius of the Earth, 6.37 times 10 to the 6. And at the end of the day, this is 6, this is 6, this is 6, and this gets squared. 6 times 10 to the 6, but this gets squared. So this gets 6 times 6, cancels that 6, cancels that 6. This becomes 6 to the 12. This 6 to the negative 11 comes downstairs to 6 to the 11. And then you have 10 to the 24 divided by 10 to the 23. You get 10. You know what I mean? So that's the acceleration of gravity, 10 meters per second per second. Okay, so that's that side of the equation. And then they say, hey, this acceleration is the acceleration of gravity of 9.81. So then instead of doing that, they just say, hey, we know that, and we're near the surface of the Earth, so our weight force, this is like F, it's a mini version of F equals ma. Okay, cool. So, and it's because we know the acceleration of gravity, and multiplied by our mass, that's going to be our weight. That's the force that's caused by the acceleration of gravity. Cool. And it's just this side of the equation too. That's the bizarre thing, is that you have F equals ma, but like I would put this Fg as a force into this side of the equation. But when it comes to it, you're also saying that the force, like this is the acceleration part. So I don't know like where it gets confusing. You know what I mean? Where like I would put the force of gravity. That is a known force. That's in this side of the equation. You know what I mean? Even though if all you're doing is finding the force due to gravity, it looks like it goes in that side. You know what I mean? Because you're just like, well, the force of gravity is my weight is g(m)me divided by the radius of the Earth squared. And in this case, it looks like it goes in that side. All right, so but here's probably the reason why it doesn't go in that side, because this F equals ma is a summation of the forces. You're using your textbook to find all the forces in the known universe, and once you have summed up all the forces in all the directions, you know what I mean, then you might have a net force, a force net. And then you have this mass, like you, that you're, or any object that you're trying to figure out if it has motion and if it has a change in velocity of that motion. And so this is what you're trying to analyze. You're trying to like get this acceleration as a summation of the forces divided by the mass, and now you have an equation for acceleration. And that's the reason why you would not put this force of gravity into this side, because then you just bugger up the equation and you lose this acceleration as a function of the summation of the forces, you know what I mean, to get that force net. Because we're going to find out that, yeah, in a lot of cases, the force of gravity is not your only force. Because now we're on a spinning Earth, we do have some sort of omega. And so that's causing an acceleration in the normal direction. So now I guess the only question is, like, hey, what side do you put that on? I mean, do you say, hey, the force due to this acceleration is going to be just the mass times the acceleration in the normal direction, and that's going to be the force, the centripetal force, you know what I mean? And that's what we're going to find out. That's why I definitely have to do this problem like every time, and we'll get to it hopefully right now. But yeah, so if you don't have any rotation and you just are on top of the North Pole, you're not getting flung off. You're not at the equator, and you just have this force of gravity, which is mg, and then a normal force. And the reason why you have a normal force that's equal and an opposite is due to F equals ma. You put eyeballs on this thing, and we don't have a change in the velocity. We're not flying upward, skyward, and we're not sinking into the Earth. We're just totally stationary. So our acceleration is 0, but if we break out our textbook, there's a huge Earth underneath us, and so we have this force of gravity, g(m)me, radius of the Earth squared. So just the fact that we have one force over here means that we have to have a second force, because we already observed that we don't accelerate. You know what I mean? So F equals ma is a powerful equation, because it says either if this is some number, if your acceleration is some number, that means you have to have a force causing that acceleration. Cool. But if your acceleration is 0, well, then you have to do some investigation. Break out your textbook. Are you like in deep space where there just really is no forces, and now you're experiencing some sort of crazy acceleration? Well, you got to account for that. Maybe you found something new. But for us, it's just like, no, we're on Earth. We have a huge Earth underneath us. So on this side, we at least have the force of gravity. And now since we have one force, F equals ma would say, no, we should be experiencing a change in velocity. But we don't through observation. You know what I mean? We're just standing on the surface of the Earth. We're not moving up or down. So now what gives? Well, you must have an equal and opposite force. And that's what they call the normal force. And I think it's, I don't know, kind of I think it's like, oh, well, that's easy. You know what I mean? It's easy and horrible all at the same time. I swear, it's like, it's not intuitive until you say, hey, we definitely have a force of gravity, and if we're not experiencing acceleration, there must be an equal and opposite force. So I mean, so it is Newton's equal and opposite force deal. It's just, that's what we call it. We call it the normal force. And so in this case, well, cool, you have the force of gravity, which is mg, and now you got to pick a direction, you know what I mean? How about the center of the Earth is the negative direction, and skyward is positive. So we have a negative mg. We have a force in the direction of the center of the Earth, and then we have a normal force that's in the upward direction. And now this is going to equal ma, our mass times our acceleration, and our acceleration is 0. And so cool, this equation just becomes our normal force is equal to mg. Alright, so that's the simplest case. Now, if you're a skydiver, they do the second simplest case before we move on. You still have a weight, mg. It's just there's nothing underneath you. There is no normal force. So now you have negative mg is equal to your mass times acceleration. And so that's what it was. It was F equals ma. We put the forces in the known universe over here, which was that weight. And if you don't write it like this, you can always write it like force of gravity is G-M-M-E divided by radius of Earth squared. That's what you'd put in this side, and you'd say that's equal to mass times acceleration. Cool. And so now if you wanted to solve for acceleration, you would just say, hey, our acceleration is negative g, and in this case g would just be 9.8 meters per second. All right, so and that's going to be trippy whether g, if you say g is negative 9.8 meters per second squared, well then how the hell does that work out? Because we just said we had a force in the negative direction, you know what I mean? So that part screws with me, you know what I mean? Because we already said we have a negative force in the negative direction. That's bizarre. But anyway, well, let's move on. And so what we're going to get to is like, hey, let's spin the Earth and we're on the equator, and why do we feel lighter? And we don't feel lighter by much. So I'm going to say 2.2 times 70. Yeah, I'm going to say I weigh 70, or my mass is 70 kilograms. All right, heck yeah. And so my weight is mg, so that's 70 times 9.8. So I weigh, my force, my weight is 686 newtons. Now, the radius of the Earth is 6.73 times 10 to the 6 meters. That means the circumference of the Earth is 2 pi radius of the Earth. Cool. And let's put this into our calculator. Alpha r is 6.73 million. Circumference is already in there, but that's 2 pi alpha r. So I save that as no, I didn't save it. So we got 2 pi r. Store that as circumference. Cool, so we got the circumference of the Earth. And then we want to know how fast the Earth rotates. It's not a 24-hour day. It's 23 hours and 56 minutes and 9 seconds. Cool. And so we're going to go 23 times 3,600 to get that many seconds, plus 56 times 60 to get that many seconds, plus 9. And do I even have this stored as alpha t? Close enough. I didn't add the 9. I think it's like 56.4 seconds. I don't even think it's 9. But now I just don't remember. But I'm just gonna say it's plus 4. So that's what we're gonna use. We're gonna use 86,164 seconds. So this is one rotation. We're gonna store that as alpha t. And I got a pretty decent visual for this, you know what I mean? So if the sun is here, and then we just rotate in a circle. I can't make my whole hand like rotate all the way around. But I'm going to say, hey, this is high noon. You know what I mean? You're standing right there. You're facing high noon to the sun. And then when the Earth rotates 360, just imagine we're back to high noon. But what happens in a day is that you actually rotate around the sun like this. You know what I mean? you just move this way. Well, look, now you're not even facing the sun anymore. You have to rotate an extra 4 minutes for high noon. You know what I mean? So this happens every day, that the Earth has to rotate an extra 4 minutes, you know, just to like get back to high noon. And what happens is that causes the Earth to rotate one full rotation. You know, this is where if the moon is tidally locked with the Earth and it's doing this around the Earth, well, technically, if you just look at the moon is rotating once in 27 days. So the rotation of the moon is once per 27. It just looks bizarre that it's rotating out here. But if you had a camera on top of the moon, you would see that it's just rotating. You know, and you weren't looking at anything else, but it's rotating around the Earth. So the Earth does that around the sun, but you get an extra rotation. So any planet that spins around its axis and then also spins around something else, the moment that it spins around that other thing will have rotated another time. So yeah. So in a year, there's 365 days. There's 365 of, like, you know, high noons, you know, rotations to get all the way around. But in that process of catching up, you do one extra full rotation. Cool. So that's why a day is a little bit short. A day is 24 hours. Because again, you're facing the sun, high noon. And then in one 23-hour, 56-minute, you know, 4 minutes less is like, hey, you should have been facing the sun, but then you're also rotating this way. So it takes that extra 4 minutes. And so where this number comes is you take that extra day, 24 hours, times, well, what do you do? What do you do? Yeah, you say, hey, let's say there is 24 hours in a day. That's 3,600 seconds. And then times 365 days in a year. So you have this many seconds. But you have to subtract... bummer. But you... So in that amount of time, in 24 hours, in this many seconds, you did not, the Earth spun 365 times. So then you divide by 300, the Earth spun one more time. So you take that time that you thought was 365 days times 24 hours, you know what I mean? And so that seems like the time for 1 year. But you didn't rotate 365. You rotated 366. So you take that time divided by 366. Cool. Now you have this new time. That's 86164. So yeah, so it is 4 seconds. You know what I mean? So if you can't remember this, just take 365 days times 24 hours times 3,600 seconds, which is kind of the definition for 1 year. But I think it's 365.25. It doesn't matter. You could do that. 365.25, because you get that extra quarter day for that leap year, you know what I mean? And then you're going to multiply that by 24 times 3,600, and so that's how many seconds. But now you're going to divide that by 366. Cool. So then you get 86. Oh, but no. You can't. You have to divide it by 366.25 as well. So you have to take that divided by 366.25, and then you get right back to that number. Or you'll get back to this number nonetheless by taking 365 times 24 times 3,600, then divided by 366. Just by happen chance, you get the same number. That's a wrong association. You have to say that a full year from basically spring equinox to spring equinox is, and that's based on the stationary position of the stars. But yeah, that's going to be 365 and a quarter days. All right, sweet. So that's out of the way. That was just to say, cool. 4 minutes. Who the hell cares? And because it's really insignificant. It's just fascinating. But this is the time that it takes for one revolution. So then, what are we trying to find? Well, we're trying to find the Earth's rotation in radians per second. You know, even that. What the hell is a radian? You know what I mean? It's 60 degrees. It's if you took a string that was the radius of the Earth and then draped it around the Earth, you would get about 60 degrees. And there's going to be 6 of those in a circle. Basically, almost 6. 6.28. That's 2 pi. All right, so so you're going to have, hey, 2 pi radians. That's 1 revolution, and you're going to have that in a hell of a long time. 86164. So I'm going to store that as my alpha t, and I'm going to go 2 pi divided by alpha t, and so this number pops up, basically 7.3 times 10 to the negative 5 radians per second. Hella slow. And so if this is our, what was our acceleration normal? Well, that was going to be negative, our radius, and then our radians per second squared. That's going to be our acceleration normal. Well, we found our W, found our omega, our radians per second, our angular velocity. We know our radius, that's the radius of the Earth, so we can find the acceleration due to this spin is going to be the radius of the Earth, and I'll put a negative on it. I don't really like the negative. Alright, heck yeah. But that's our goal today, is like, hey, let's figure out this negative, and we got this F equals ma. We need to figure out what side of the equation we need to put that in. You know what I mean? I'm still not 100% positive. Alright, so this is R in our calculator, and this is W. I'm going to store that as alpha W. And so we have negative alpha R, alpha omega squared. And then so we get an acceleration due to the spin of the Earth. We get an acceleration of negative 0.003. I'm just going to say 58. And this is in meters per second squared. Now what would you compare this to? Well, you'd compare it to 9.8. You know what I mean? So if you were experiencing 2 Gs, that'd be 9.8 times 2. You'd be experiencing 19.6 meters per second. But you're experiencing 0.035. I'm going to store this as alpha A. And so that divided by 9.8, yeah, you're experiencing 3 to 4 thousandths of a gravity. You know what I mean? So it's just nothing. And that's where I just made the association that if something's spinning, you know you're going to get flung off. I think just visually you can see that. And so then you can use F equals ma. This is how I would use it. I'd just be like, well, the force that you know, maybe you're getting flung off with is your mass, 70 kilograms, times that 0.0036, 0.0358, my apologies, and we got times 70. And so we get a force of negative 2.5 newtons, and divided by 4.44, you know what I mean, this is a half a pound. So 8 ounces, you know what I mean. So I've always said if you move to the equator, you're going to weigh 8 ounces less. And so that's just a good one to have in the back of your mind. You're like, oh, sweet. So the average person, you know, might weigh 8 ounces less. Very heavy person would weigh a whole pound less. So yeah, that's pretty cool. The other scenario, this is solely just due to the spin of the Earth. You didn't move to a higher elevation. You're still the same radius of the way. Gravity is still the same, the gravity of mg, but you're getting flung off. You have a velocity around a circle. Things are just wanting to fly off like a merry-go-round. And you know what I mean? And so because of that, you're kind of stuck to the Earth because there's a gravitational attraction between you and the Earth. It's like a magnetic force, you know what I mean? It's kind of, it's like two magnets attracted to each other, and And if you had that, if you had like two magnets, these aren't magnets, but if you had these two magnets attracted to each other, but then you spun them at a high speed, well, due to this thing we're talking about, they're gonna fly apart. So you're gonna get that to happen. And that's just where I think people hold their tongue because they don't want to say the wrong thing of like, oh yeah, there's a force that's pushing these things apart. Because I guess there's some wrong ways to think about that. So now what we're going to do is finish that. So we got F equals ma. And we have now our person standing on the earth. And we do have a normal force underneath us. We have the force of, we have a weight. We have mg downward. And we also have something else. We have this acceleration in the normal direction that's negative omega, negative r omega squared. And I actually don't know. You know what I mean? Do you put this on the acceleration side? Yes, that is what you do. Holy Toledo! You know, it took me to this point because hey, we have to throw eyeballs on this, and you might not see it though, because you don't see anything. You know what I mean? But let's say, yeah, this is north, and then you have a bird's eye view of the Earth. What it looks like to a observer looking down on the Earth is like, hey, you have tangential velocity. You should just be moving that way. But you don't. You're moving towards the center. So every time you move in a circle, and again, that's why we started out, because this is kind of a hidden acceleration. You know what I mean? It's not very obvious because it's like a change in direction. It would be like, hey, if I have velocity in this direction, but then at some point I change my direction, and that's all I do, and I still have the same velocity. Well, do I have an acceleration? Hell yeah. And it's that same thing. It's the same thing. Do I have velocity at this point? Do I have any velocity that way? No, my velocity is 0 that way. But at this point, you know what I mean? I mean, because like at this point, do I have any velocity that direction? No. You know what I mean? At this point, do I have any velocity that direction? No, because my next location is in this same direction. So this velocity equals 0 happens just right before this transition. And then the same thing. You traveled a distance d in a change in time. Let's say this is just 1 second. Well, your average velocity in this direction, velocity average in that new direction, that tangential, or like just a new direction, is going to be that distance change in time. But we don't have any velocity in that direction, so by that axiom, our V max, or basically our change in velocity that we're trying to find, is 2 times the velocity average. And our acceleration is that change in velocity divided by change in time, by definition. So now our acceleration in that new direction is 2 times the velocity max divided by that change in time. Heck yeah. And, 2 times the velocity average, which would be 2 times the distance times the change in time squared. So there you go. So this is the acceleration due to just changing direction. And then so if I'm an observer up here, it's hard to see, but no, I am witnessing acceleration. So anytime anything's moving in a circle with motion and it's in a circle, or just anytime you have any motion that's not linear, you have an acceleration. You have an acceleration in the direction perpendicular to that motion. Cool. So yeah, so it does go into this side. So now we can sum our forces. We got negative mg down plus our normal force up, is equal to our mass, and I have no idea. The signs might not make sense, and then I'll have to just reiterate something different. But that made sense to me. We observe acceleration. This is our acceleration. We have no other acceleration except this one. But that gets me kind of interested in, is there problems where you could have an acceleration due to this rotation, and then an acceleration due to this omega having an angular acceleration, alpha? Because then if you had an angular acceleration... no, we're good. Because you have to... in these problems, you're saying, hey, if I'm on a circle, well, there's only two directions I'm going to choose. I'm either accelerating in the normal direction, or I'm accelerating in the tangential direction. And yes, if we change this alpha, we would have experienced acceleration, but only in this direction, this tangential. What we're seeing is that change in direction, which is an acceleration in that normal direction. That's why this one is hidden. Now, we could just be experiencing, because the other thing that we could be experiencing is we're just in an elevator for the first couple seconds. You know what I mean? So you could be on the equator in an elevator, and then also in 1 second be moving upward. You know what I mean? And you could be moving upward actually with a change in velocity that was pretty hella slow, that would be equal to so now if my velocity is increasing that way, I have an acceleration. Alright, hell yeah, I would have an acceleration in the positive direction. And we're saying 0, 0 is the radius of the Earth, you know what I mean? So we're saying our origin is 0, and for this one, you know, our angle right here is 0. So we have radius and theta. That's going to be the polar coordinates. But this is 0, and heck yeah, this is some plus. This is our positive direction. And so in that case, we would have acceleration in the positive direction. And they're additive. So this is blowing my mind too, because you have this idea of summing forces. We're so used to that in statics, but then we also use it as vectors. And I think for whatever reason it gets lost on me that when you add vectors, you know what I mean? Hey, A plus B, you know, and now you have a new vector C, or you just have A plus B. But then you have the component of A in the x direction, AX, and then you have AY, and then you have this component of BY, and then you have this component of BX. And then so if I'm just solely working on the components, it looks like AX plus BX, if I'm adding these vectors, is this one plus this one. So I would go this one plus that one, and then this is my resultant of AX plus BX. And then if I did AY plus BY, I would do this one plus that one. So that one plus that one, and now here is AY plus BY. And yeah, it's just fascinating that is fascinating. That I could do all of statics where I'm just summing the forces in the x direction and saying that's equal to mass times acceleration in the x direction, crossing this out because I'm doing a statics problem, and then just getting on with life. But yeah, it's like, whoa, I didn't understand from that perspective that I can also say I'm summing the forces in the x direction, and I might be experiencing some sort of acceleration in the x direction. But this equation is totally separate compared to the force in the y direction is equal to mass times acceleration in the y direction. This is why projectile problems, they usually don't have acceleration in the x direction. But you do have acceleration in the y direction due to gravity, usually in that negative back towards the center of the Earth. And so... but yeah, that's the bummer part, because if you do have that acceleration, you would say, you would say this. You would say the acceleration due to gravity is g, and g is negative 9.8. Because then it would reverse that vector. Yeah, it's so bizarre when you actually draw a vector in the negative direction and then say, that makes g positive 9.8, or the absolute value of 9.8 if you draw the vector in the negative direction. All right, so hell yeah. So this side of the equation, F equals ma, well, yeah, it's just these vectors are additive, and I didn't realize that I was summing forces in the normal direction. So the sum of the forces in the normal direction are equal to the mass times the acceleration in the normal direction. And you don't have to pick a direction. You could say, well, no, you do, because because if you found out that you had acceleration in the normal direction, well, you're going to add those things up in sum, and then you can get like all that is equal to the acceleration in the normal direction. If you have another equation that says, hey, you got some acceleration tangential, it's going to be the same equation. You're not going to have F equals mg. You're not even going to have a normal force. You know what I mean? You might not have a normal force, and but you might be experiencing acceleration in that direction. And so your total acceleration, your acceleration as a vector is going to be an plus acceleration normal and acceleration tangential, and these will also be vectors. You know what I mean? They'll just be in different directions. But if you want the quantity, the total absolute value of your acceleration, that's just Pythagorean's theorem. And that's just kind of fascinating that, yeah, if I have, and in this case, I have an acceleration due to gravity, and then, I got to pause on this, because gravity, we're saying, is downward, and our centrifugal is downward too. Let me take a pause. Alright, hell yeah. So I took a little break, and I'm so glad I did, because I have a way to kind of finish this, and this will be pretty sweet. So this is our acceleration due to the spin. It is very little. It makes us weigh 8 ounces less. Cool. I want to answer the question, what's 2 G's? You know what I mean? If we experienced, actually negative 2 G's. You know what I mean? So if this acceleration, so our acceleration of gravity is 9.8 times 2. So if this acceleration is 19.6 meters per second squared, we would be we would be not only weightless, we would for sure be flung off the earth. You know what I mean? And what we're going to say is that we're not flung off the earth, that we're attached with like a 3-foot rope to our feet. And then so, when we do experience this rotation, this rope is providing tension. And if we have an acceleration due to this rotation of 19.6, well, we still have an acceleration of gravity of 9.8, and because those are vector quantities, we would have a relative acceleration of just back to 9.8, but it would be in the opposite direction. So we would feel a weight that way, and the tension in this cord would be the weight of our body, you know what I mean, in newtons. So let's do that, and I think that's the most fascinating one. If we have acceleration normal is, and I'm just going to drop the negative sign until it's necessary. So we have r omega squared, and so what we want to know is when this side of the equation is 19.6, and we have this is the radius of the Earth, so we're going to do 19.6 divided by the radius of the Earth, square root that. This is going to be our radians per second. Once we get radians per second, I mean, in theory, when you do radians per second, you know what I mean, this is kind of like degrees per second. And so if it says we're spinning at 6, let's just get ready. If we're spinning at 6 radians per second, that means one rotation of the Earth is every 6 seconds. I think it'll be a little bit more than that. I know if I just did this is part 2 of the problem of like how fast would the Earth have to spin in a day to make the equator feel like the moon, like 1/6 gravity. And you would have a 90-minute day. So let's do this. 19.6 divided by the radius of the Earth, square root that, and you get 0.017. So you don't get 6 radians. You get 0.017 radians per second. And so if that's radians per second, and we want time, and we know that there's 2 pi radians in 1 revolution, I need to take 2 pi radians divided by radians per second to get that time. So 2 pi divided by that, and we get 3,681 seconds divided by 60, and we get 61 minutes. So a day would have to be 61 minutes long for us to get not only flung off, but if we were attached with a rope, for the tension in that rope to be our body weight. So if our feet weren't attached and we were actually just hanging on to that rope on like a bar, it would feel like we were doing a pull-up, or just like a dead, like whatever, you just like holding on to a pull-up bar with arms outreached. So cool, so let's do those scenarios, because this will explain, I think this will be a good way to explain normal force. So again, we're going to be standing on the Earth, but now we have a rope attached to our feet, you know what I mean? So there's the rope, here's the Earth, we have an mg, and then so now there's this normal force. But this, we're going to do like the 3 scenarios, but this will show that if we have hella acceleration due to an omega, due to a revolution of the Earth, that this normal force will be negative. And that normal force is just the tension in the rope. So this normal force will just equal the tension. And this makes so much sense, especially from like a material mechanics perspective. Is like anytime that you have like a bar, heck yeah, you got a normal force. And they always just do the forces this way. You know, this is your tensile force. And if it's positive, heck yeah, you have a tensile force. If it's negative, now you have a compressive force. Same thing for normal force. If you solve for normal force and for some reason you get a negative number, well, you just have tension on that particle of mass. All right, so finally, let's do F equals ma, and I think the sign changes, you know, will apply, but we have negative acceleration in the normal direction is negative r omega squared. We have an mg. This is the down direction, so this is the positive direction, and we have a negative mg. G in this case, though, is just 9.8. It's not a negative times a negative. And then we have an upward normal force. And that's going to equal to our mass times the acceleration in the normal direction, which is mass times negative r omega squared. So now if we wanted to solve for the normal force, because this is the only thing that matters. It doesn't matter if we're skydiving. You know what I mean? Hey, we still have a weight of mg. You know what I mean? The force, and this is kind of bizarre to think this as weight. I mean, you see this as mg all the time. So let's do it as mg, but then we can go back and be like, no, this is g m e radius of the Earth squared. You know what I mean? That's all that is. And that's just a textbook force due to 2 particles of gravity. This is just a shortcut, but it might confuse. You know what I mean? because you're just like, well, I had weight on the ground, I got that. No, you had a normal force on the ground. That's what you were feeling. It's the weight between you and the scale. It's the normal force that's sandwiching those two together that gives your readout on the scale. When you're free falling, you still have an mg. You still have that force of gravity. It's just that F equals ma. There's two sides of this. If you have a force, you might not have a balancing force. You might have a net force, and that means that you're going to observe acceleration. Now in our problem, again, we've already observed the acceleration. It's just a little harder to observe. Is the fact that we're not moving tangentially and we're moving back towards the center of the Earth. It's kind of a hidden one, but it's there. So cool. So this is our equation, and we're going to go negative mg plus n is equal to mass. I'm going to go negative mr omega squared. So now if we solve for the normal force, we say normal force is equal to, bring this mg over there as a positive, and this is the bigger one, minus mr omega squared. And then you see that the normal force is our weight minus that acceleration. So that's how that gets minused out. That's why you feel less weight. It's because the normal force is less. You still weigh the same, but the normal force is less. And in our case, this part of the equation is stored in our calculator as A, and we got, and this part's 0.0357. And the whole thing is, even the negative part. So we have negative 0.0357. And so we're going to do the mg. I'm going to say 170 times 9.8. 70 times 9.8. So my mass is 70 kilograms times 9.8. So our newtons is 686 newtons minus this acceleration times, so this would be 70 kilograms, negative 70 kilograms times 0.0357. This negative is associated. Those are all one number. That's the acceleration in the normal direction. And then so we have 70 times alpha A. So we have negative 70 times alpha A. And this, whoa. Oh, bummer. I lost my value for that. Okay, so there we go. 70 times alpha A. And we get negative, we get minus 2.5 newtons. Yeah, remember that 2.5? It's 8 ounces. So now our final newtons, minus 2.5, is 683.5 newtons. Cool. So 70 times 2.2 was 154 pounds. And then this times 2.2 is, whoa. This times 2.2. No. Oh, I apologize. No, I'm going the wrong direction. If I'm at 686, I divide by 4.44. And that's 70 times 2.2. Those are the same. So 683.5 divided by 4.44. So we go from 154 to 153 like 154.5 to 154. Cool. Yeah, you drop a half a pound. Now, in the case where this acceleration is hella, we're going to have n is equal to mg minus mr omega squared. Now, this part plus the negative, we're going to say that's negative 19.6. So now we have negative n is equal to mg minus m times 19.6. And then so we have n is equal to our mass, 70 kilograms, times 9.8, minus 70 kilograms times 19.6. And so, yeah, 70 times 9.8, there's a lot I can just factor out, but minus 70 times 19.6. and we get negative. Our normal force is negative 686 newtons. That was our initial weight, and now you see that the normal force is negative, and if we are attached to a rope, heck yeah, that's gonna be tension. So that's something that a lot of physics books probably do not do. They don't say, hey, your normal force might be negative. You know what I mean? It happens in material mechanics. Well, whether in material mechanics, whether you're tensioning something or compressing something, it's still a normal force. It's a force in the normal direction. Normal just means axial force. Yep. So yeah, that's fascinating. So yeah, you can have a normal compressive force or a normal tensile force. Yeah, it just doesn't get described so much in physics. That your acceleration can be so much that, yeah, you don't experience. I mean, I guess they would just say, I think physics books would just say, well, you don't have a normal force. And, but yeah, that's the case. You don't have a normal force, and now you do just have some sort of change in velocity. Your acceleration in that direction is you know, now you're a rocket. But in our case, we're going to be attached by a rope. So yeah, a negative normal force is sensical. But if you're not attached by a rope or anything, no, and you're just a free mass particle on the surface of a huge Earth, well, no, you're gonna be no longer attached to the Earth. Okay, hell yeah. So that was pretty sweet. That was pretty sweet. Alright, so hell yeah, let's do one more example and kind of play around with that negative sign. The next thing I'm going to do is like the Gravitron, you know what I mean? The fair's coming up, and you have all these people, and they're on the side of the wall, and you know what I mean? There's their arms and stuff, and they're like, whoa. And so we have an omega, and now, you know, we're just going to say that acceleration in the normal direction, we got that figured out, is negative r omega squared. Hey, let's just set that to 19.6. That was pretty sweet, because now we know that this acceleration is going to feel like 2g. And in this case, we have a bird's eye view, so gravity is downward, so there is no, in this radial direction, there is no, you know, mg going back towards the center. And so this will be an experience where your body will experience 2g's. You'll get sucked up against the wall with 2g's of force. So now, and we're going to do both things. We're going to be like, well, hey, there's one scenario, and then the other scenario is the merry-go-round. And maybe you do have a bar, and then you're going to be hanging on to this bar with some rope, and so there's going to be some tension in that rope. Maybe we'll just do one rope. I don't know. Anyway, and we're going to do both these scenarios. So we're going to say F equals ma. Well, they're so one, do we observe acceleration? Hell yeah, because we're not observing linear motion. We're observing motion in a circle. So we know that acceleration in the normal direction. You know what I mean? Like we should be going tangentially, but no, we realize that we're not. It's that same scenario. It's like, hey, I have this velocity. This is my velocity tangential. But now I'm over here now. You know what I mean? I'm still going velocity tangential, but did I have a velocity normal? You know what I mean? That is the question. Like right here, I had velocity normal is 0. I had no velocity in the normal direction. You know what I mean? So like right here, I am not moving towards the center, but I do have hella velocity tangential. Right here, I also have hella velocity tangential, but it's in a different direction. Same scenario, and whatever this distance, it seems imaginary, but if this is a change in time of 1 second, well, sweet. Our velocity average is d divided by 1 second, and then our velocity max to do that is 2d divided by 1 second. That's our change in velocity. Our acceleration is that change in velocity, change in time, which is divide by 1 second again. So that's where time gets squared. And then you find the acceleration, 2d divided by 1 second squared. Okay, so that's the visible acceleration, and we call it acceleration in the normal direction. And so in this case, we still have a normal force. That's the bizarre thing, is that even if we're just sucked up against the outside of something, well, we might. And this is cool if you do this, because let's say whatever you're getting sucked up to, you're also glued to. You know what I mean? Because just because like you're on the Earth, your feet might be glued to the Earth, and so the Earth could be spinning so fast that you would have got flung off, but your feet are glued to it. So your normal force is negative. You know what I mean? You're going to experience tension. Negative normal force must be tension. So in this case, our normal force is that direction. You know what I mean? So it's in a different direction. Alright, hell yeah. My camera overheated, but we're back. And man, well, let's just get on with this. So we have the normal force. That's going to be what we're pushing up against in this ride. So now we don't have any gravity, but we have, and we're going to say, hey, this is in the negative direction. So we have a negative normal force, how we drew it. And that's going to be our only force. You know what I mean? So we sum the forces, that's it. And no other forces. But now we come over here. F equals ma. We know the acceleration. So we have mass times the acceleration in the normal. And that's going to be negative m is equal to m negative r omega squared. Cool. And then so we have two negative signs. So now we just say that n is equal to mass r omega squared. Our normal force that we will feel in that direction, or just this normal force that is is our mass, 70 kilograms. And then we're just going to say, hey, we just already assumed this was 19.6 meters per second. We're spinning hella fast. So we got 70 times 19.6, and you get 1,372 newtons divided by 4.44, and you get 309 pounds. So divided by 2, if I weighed 154.5, now we have 309 pounds. So this is the normal force that we would feel with 2 G's. And you can figure out what speed, angular speed, by figuring out what this radius would be. And you can do that. You can design an amusement park ride to achieve a certain g-force. All right, so in this case, now we're saying, it's the same thing. We know we're getting flung off, but maybe we don't know that. You know what I mean? Hey, because it's the same thing as like, hey, I'm doing a handstand on top of the Earth. You know what I mean? This is the North Pole, but this is the equator. We're still spinning, and now I can't tell both these pictures. I can't tell if I'm being flung off. I know I'm being flung off because I do have some sort of angular velocity. You know what I mean? So like the act of getting flung off is happening. We just don't know how strong it is. So we still have to pick a direction for our normal force. And normal force is always, well, where your mass meets up against, like normally, in a perpendicular direction to the other chunk of mass that you're dealing with. So even in material mechanics, I might have this, and I take a cutaway, and now I want to know, like this cutaway, I want to know, well, what's the normal force on it? You know what I mean? So I would say, And then so here, if I took that cutaway, like here's me, like I cut myself away. So this is the cutaway that we're taking, and I'm gonna say, hey, I have an mg, but now we have a normal force in that direction. So there you go. So that we have a normal force in this direction. But in material mechanics, they actually don't do it that way. They say your normal force is in the tensile direction. Yeah, material mechanics is bizarre too, because, I mean, you have something like this. You have a positive x direction, and then you have a negative x direction. But guess what? This tension is equal to that tension. Tension is the absolute value of that number in both directions. You know what I mean? So that's just by sign convention. So I'm sorry I brought up the material mechanics up, but those are things that you'd be like, well, where did that come from? You know what I mean? Why isn't this tension? Yeah. So that's kind of interesting. All right, so I'm just going to choose in both these scenarios the normal force in that direction. And then we have our mass. And I guess I should talk about, yeah, let's do both those. Because one is a merry-go-round. This is the merry-go-round. And then the other is the Earth doing a handstand. Now, the free body diagrams, you know, you do cut the object out. So I am going to cut that out. And I do a pretty good job of free body diagrams, you know what I mean? I say, hey, you're just in deep space. There's nothing around you, you know what I mean? And then so that's number one. Number two is that well, I mean, yes and no. I mean, you still have you still have F equals ma. You still have this textbook side. You're like, hey, can we observe forces? Well, sure. Like in this view, before we did the cutaway, we established that we do have a weight of mg. You know what I mean? So we already know that. But now you do the cutaway. The second you do a cutaway, hey, that force still stays. You still have an mg, but now we have a force. You know what I mean? Weight is a force, and it's in that direction. So if you do cut this away and pretend it's in deep space, well, this little human is going that direction with the velocity and a change in velocity. F equals ma is going to keep speeding up, you know, forever. But F equals ma, we observe that we in this case, hey, maybe we don't have, you know, with the non-spinning circle, we don't have any acceleration. You know what I mean? So that goes in this side. But in our case, we have the textbook side that says, yeah, we do have gravity, and then we do have this. Well, no, we are spinning in a circle. So we have negative r omega squared on this side. You know what I mean? And by the observation side. But these forces are mg, but we also know you do get a normal force anytime you're touching a surface. You know what I mean? If you're touching a surface that you just cut away from, you will have a normal force normal to that. Okay, so we have the normal force up, and then mg down. And hopefully it's the same in material mechanics. You know what I mean? If I did take that slice. Is it not? Is the normal force not into, because that's the compressive direction, you know what I mean? So, yeah, I'll have to review the material mechanics. But in this case, hell yeah, normal force is just perpendicular to the direction that object is touching. And so now we can do our F equals ma, where we're going to say this is the positive direction, this is negative. So we have n minus mg for the handstand on the Earth, you know what I mean? And then we're going to say, hey, the Earth is moving hella fast. So we have the handstand on the Earth. Earth is moving hella fast, and we have that equal to the mass times the acceleration in the normal, which is mass negative r omega squared, which is mass times 19.6. And so we have normal force minus mass times 9.8 is equal to mass times 19.6. Cool. So we're going to bring that. My bad. This is negative. You know what I mean? This will be a negative number. And then so we'll have normal force is equal to m negative 19.6 plus, because the sign changes, mass 9.8. So there you go. So we're going to feel a normal force of m negative 9 point, m negative 9.8. Minus 19.6 times m is plus m times 9.8 is going to be a negative 9.8. So we have 70 kilograms times negative 9.8. And we get that negative 606. Alright, so we get negative 686 newtons. Oh, this is going to drive me insane. Oh, no. We're good. Because we get a negative for our newtons, it must mean that we have tension. You know what I mean? It must be that our hands are glued to this earth, and in this case, we actually are getting flown off, and we feel tension. So that's that. So that's where the normal force would be negative. And that's the force that we feel. Now this one, the merry-go-round, we're a bird's eye view. So our weight is mg down, but using vectors, we're not interested in that direction. We're interested in any change in velocity in this direction. We're spinning, and so we've identified a circle, and we know that around a circle, you always have that change in direction. You know what I mean? Going back to velocity tangential and then velocity tangential. You're going to have a velocity normal, a change in velocity normal, change in time. And that's what we experience, and that's going to be the acceleration in the normal direction, negative r omega squared. Cool. So our F equals ma for this case is, you know what I mean? Let's chisel this human out, in outer space. We don't have any forces, but we do have a contact point that we cut away from. You know what I mean? So just like material mechanics, when you actually cut away a face, then heck yeah, you get a normal force. You get a moment, right hand rule moment, and then yeah, you get a normal force and a moment. You also get a shear force. And let's see if I do this right. I do the smiley face, and then so if it's on this left side, this side went down, and then so you get a shear force in that direction. Cool. Hopefully that's right. But yeah, those are the three things you get when you open up a face. So we're cutting this out, and we cut it across the surface. We expose that surface. Heck yeah. Oh, right here. We get a normal force to that surface. So there you go. So there's the normal force and no other. So, and we're saying that this is the positive direction. Normal force is in the positive direction. So we get one force, net force, normal. And if the Earth wasn't moving, we wouldn't experience any force. You know what I mean? If you're just laying next to a merry-go-round and then put your hands on the edge of the merry-go-round, well, there is no normal force axially, in this normal direction. There's not. But if you're hanging on to a very fast-moving merry-go-round, and this merry-go-round is going to be going at an acceleration of 19.6 meters per second, hell yeah. You're going to experience. So F equals ma. This is the acceleration normal side. It's negative r omega squared. And we're going to see that the normal force is equal to mass times negative r omega squared. And then same scenario. 70 kilograms times negative 19.6. And we get, but we get double it. We get 70 times negative 19.6. And we get negative 1,372 newtons divided by 4.44. And we get negative 309 pounds. The negative sign means that we're experiencing tension here, you know what I mean, in this scenario. And in this scenario, it doesn't matter how fast we're moving at all. If we're moving at any speed, because it's a merry-go-round and gravity is totally down into the page, we will always experience some tension in our hand if we're moving around. Now, the only way that you'd be able to hang on and this to move around would be like if you were going so fast your feet were flying. But I guess in an ideal situation, maybe you have this merry-go-round in winter on an icy rink and there is no friction, just a perfect day, and you're wearing like brand new coat or something. And yep, then you experience a slight tension as that wings you around. Alright, so there you go. So I think we covered normal forces, kind of interesting. Anytime you cut away a surface, hell yeah, you get a normal force at that surface. And then we've identified that, sure, if you get a normal force in the negative direction, it means your acceleration, I mean, due to spinning, you're getting flung off more than your weight is holding you in. But in this case, with the merry-go-round, none of your weight is actually holding you into the merry-go-round, so any velocity in this direction will be a tension. Your normal force will be there. But we can take a look at that one more time, because that's technically probably not the case. Because what you get is you have a circle and a merry-go-round. You know, maybe you have a lip here, or a bar, and your hands go around the bar. So now, when you do a free body diagram of your hand, you can take your hand into outer space. We'll just take one hand maybe, and now your normal force is that direction. You know what I mean? So we have a normal force that direction. And isn't that different than the direction that we chose? Because if we did that, we'd have a normal force that. So in this case, F equals ma. We have this is the negative direction. So we have a negative normal force is equal to m negative r omega squared. And so our normal force is equal to mass r omega squared. And so in this case, heck yeah, your fingers will feel that normal force, positive normal force of 70 times 19.6, which is 1,372 newtons or 309 pounds. So what gives? You know what I mean? This scenario is the same thing as being on that gravitron and your whole body weight being up against the wall. You know what I mean? Then we are obviously saying we're doing a cutaway of you taken into outer space, but we know there's going to be a normal force. Oh, yeah, normal force in that direction. Yeah, there you go. And it's going to be a positive force. Cool. And, yeah. I think I'm done, you know what I mean? I would still have to watch videos of that fictitious force, of what they're calling fictitious, you know what I mean? Because this normal force is in that direction, you know what I mean? It's balancing you from flying that way, you know what I mean? So, but we do know there is some sort of acceleration back towards the center, and so that normal force is what you're feeling. And this normal force is back towards the center. Because that's the only way, again, that's the only way to have a mass that has no friction, like to a circle, The only way to actually keep it on a spinning circle is to have a force towards the center of the circle. You know what I mean? So that is the true force, and it's due to the acceleration in that direction, in that negative r omega squared. So you have to have a force in that direction to hold you on. And we just have gravity, you know what I mean? So in this case, we have mg that holds us to this Earth, and but yeah, that's why this component of the acceleration is what's causing you to fly off. So that is the fictitious force fictitious, due to that nature. And then I forget which one is kind of fictitious. You know, is it centrifugal or what they call it? Cool. Alright, hell yeah. So I think we can talk through this last part. Where if, man. So in this case where we do have an Earth, yes, you do have a force. That's the textbook force of gravity. But there is no textbook force of centripetal, or I forget what the fictitious, there is no fictitious force, I think, in either direction. But what we do have is an observation of acceleration. You know what I mean? You do have acceleration towards, you have a change in velocity towards the center if you're on a circle. And that's the if. If you're on a circle, spinning in a circle, you have to have, by definition, you have a change in velocity. And the only way, so that's that side of the equation, and it's towards the negative direction. And the only way to stay on the circle is to is to have a force that keeps you on that circle. And that force can either be the gravitational force that's holding you to that circle. It could be glue on your feet. It could be your hands holding you to a rope on the Earth as it spins. And that's the same. But it's, yeah. So what I like to do is, like, hey, let's say you're just floating in outer space, and then all of a sudden you see a rope. You know what I mean? And you have a little sign that says grab on, and then you grab onto the rope, and this rope, you hang on for 24 hours. And then 24 hours later, you actually go by the sign. Well, you just went in a circular ride, and in that ride, you had to have a change in velocity towards the center. That change in velocity, change in time, means you had an acceleration normal. So you had a normal acceleration towards the center. F equals ma. This side was towards the negative side. And then so you must have had a force in that negative direction. You know what I mean? Holding you along the circle. And if we look at what's holding you there, well, this is you, and your arms are outreached. And what are you grabbing onto? You're grabbing onto a rope. And ropes have tensile forces, you know what I mean? So if you did a free body diagram of just you would have a tensile force holding you into the circle. And this is what's required to make that ride. And then so yeah, from this perspective, I get it. People think that the centrifugal force, or the fictitious force, is a force in that direction, force fictitious. But it's to ride a circle. You know what I mean? When there is no gravity, or gravity's down into the page because you're just like on an ice rink with a merry-go-round, then you have to hang on with some sort of tension. and you that's that force that's pulling you back towards the center, so your velocity can change towards the center of the radius. So you can have some sort of change in velocity, change in time towards the center that gives you acceleration. So yeah, this was fascinating, because not watching a YouTube video on like, hey, what are they saying is the fictitious force? Just by like, hey, what do the equations say? And then just go with that. You know what I mean? And so yeah, so there you go. To ride a circle, you have to have some sort of force that's pulling you to the center. Now that force can be on this side, or that force can be on this side. And technically, like mg, like let's say you're just laying on the Earth, kind of is, I mean, both are the same. They both act on you as a mass, and they're both in that direction, whether they, you know, come from top down or you know, bottom towards it. So anyway, all right, so I think I'm done, and I think we did a pretty good job of giving some words to that, and definitely using the normal force. That was clutch. You know, anytime you do a cutaway free body diagram, you opened up the surface, you're going to have a normal force on whatever that was. And heck yeah. And then, yep, so we did it. I'm done. I mean, there's plenty of ways to get confused. I'll do more of this just to get more solid. But thanks for joining me, and that's a video.